Meeting is being recorded.
Okay.
Good morning and good afternoon, everyone. It's my great pleasure to welcome you all to this special session on modern trends in fractal geometry, organized under the auspice of International Society in Quantization, Geometry and Dynamics. ISQGD provides a vibrant global platform that brings together researchers, students, and scholars to exchange ideas, present new developments, and foster collaboration across diverse areas of mathematics, including fractal geometry and its interdisciplinary application. Today's session reflects the evolving landscape of fractal geometry, highlighting both theoretical advances and emerging applications. We are fortunate to have an excellent lineup of speakers who will share their insights and recent research contributions. I warmly welcome all our distinct speakers, participants, and attendees from across the world. Your presence and active participation are what make such academic gatherings truly meaningful. I hope this session will inspire fruitful discussion, new collaborations, and deeper exploration into this fascinating field. Thank you all, and let us begin the session. Harsha?
Yes. Yeah, good morning, everyone. Today, our first speaker is Professor Karoli Simon. He is the Professor of Mathematics and Head of the Department of Stochastics at BME, Hungary. He also serves as Head of the Hungarian Research Network BME Stochastic Research Group and Head of the Doctoral School of Mathematics and Computer Sciences at BME. His areas of expertise include fractal geometry, dynamical system, geometric measure theory, and complex networks. He has made significant contribution to the study of fractals and related areas, and his work is widely recognized in the mathematical community. We are delighted to have him with us today. Thank you, Professor Simon, for accepting our invitation. And over to you, Professor, please.
Thank you very much for inviting me for this online conference. Thank you for the introduction also. And I would like to talk about a project which is very close to my heart, which goes back to many years when we considered some random perturbation of iterated function systems, first together with Boris Solomiak and Yuval Perez, and then Thomas Jordan and Mark Polycott. But I am going to talk about now more recent results, but we should just start. So we will consider today iterated function systems which are self-similar and they are on the line. So this is a very simple setup. Such an iterated function system consists of finitely many mappings. This cardinality of the mappings during this talk is always capital L. And so they are contracting affine mappings on the line. So lambda I is the contraction ratio, which is in between -1 and +1 strictly, and not zero. And Ti is the translation. And we know we know a lot about this kind of iterated function systems. Still, there are some open problems. One of the exciting open problems is, do we have a self-similar set? The self-similar set is the attractor of such an iterated function system. We know the attractor is what remains after infinitely many iterations, starting from a big interval which is sent into itself by each of these mappings. So do we have a self-similar set on the line with positive Lebesgue measure and empty interior? This is an open question only on the line. In higher dimension, the answer is, and this is interesting. And we do not know what the answer is, but we will consider somehow the same question. So some kind of random perturbation of self-similar sets And for this perturbation, we ask the same question, whether it's possible that the Lebesgue measure is positive, but the interior is empty. The random construction is a little bit complicated, and I would like to explain it for the possible simplest fractal, which is the triadic Cantor set. So the triadic Cantor set is the attractor of this red iterated function system that you can see over here. S1 of x, I forgot to write, of x is 1/3 x, and S2 of x is 1/3 x plus 2/3. And then, well, we know everything about this set, but nevertheless, this is going to be the place where I first explain the random perturbation as we consider it here. So given two numbers, θ1 and θ2, and random variables, y1 and y2, which take values from negative θ1 to y1 takes values from this interval, and y2 takes values from this interval, respectively. And we assume that these random variables have density, which are continuous, bounded, and which are positive within these intervals. So that something like you can consider, or you can think of, as a uniform distribution, for example, within this interval, and uniform y1 uniform distribution here, and y2 uniform distribution there. That's one possibility, just to think of something precise. What we do not assume, there will be two kinds of results. One result of mine and my co-authors, Michel Decking and Nora Sekeres and Seke, this in our setup, we do not assume that they are independent. We assume some independence, but it will be unfortunately more complicated. But there will be another result, what I'm going to mention, by Barany and Roms, and in their example, it is assumed that y1 and y2 are independent. But some independence we, of course, need to require. It will happen a little later. I will be more specific about that. So what is the random perturbation of this triadic Cantor set? When you define the triadic Cantor set, you need to consider this kind of iterates which appear here. And then this is S1, this is S2. So you need to consider such an iterate when you consider the deterministic set. Now, when you consider that, when you define when you define the random copy, then instead of this deterministic function, which is either this or that, so instead of that, we replace it with a random mapping, which random mapping is simply the original mapping plus an additive error. So this is just an additive error. And then in the simplest case, this is an independent copy of yik. But as I mentioned, we consider a little bit more general case. So about this, the independence, I will talk about more. In a special case, all of these random errors are independent, but we don't need to assume that. The random perturbation in this way is the random perturbation of the original iterated function system, which gives us the triadic Cantor set in this way, this f, which is f1, f2, which is the original deterministic function plus some random error. Now the general definition is like this. We consider this similar iterated function system on the line. Lambda I are the contractions and T are the translations. we use this shorthand notation SI1IL is this composition, and lambda I1IL is this product. And if you use this shorthand notation, then when I is equal to I1IN and I write A for the alphabet, so A is the alphabet which consists of the integers from 1 to L. So this is just the n tuple of integers from this alphabet. Then Si is this when this lambda is defined over there. So you can just compute it very easily that this n fold iterate looks like this. And then this is lambda I, and this blue part, the translational part, is denoted by pi. I'm sorry. And then what is the random perturbation of S? We just add this random error. Why? Then YR is a random variable which takes values from this interval, and the density is bounded and continuous and not zero on this interval. So how we iterate these random functions? In every step, we just add this random translation error, what you see over here, and the total error is going to be small, approximately the magnitude of these thetas, because you see that here this is a function composition. So whatever you have here, you apply n minus 1 times contractions on this translational error, and that's why the effect of this translational error will be very, very tiny eventually. So if we write down what this means, it is SIX, which is this deterministic part plus this red part, which is the error part, and this red part is called YI. So basically, this is how this FIX, this randomly perturbed function, looks like, the deterministic and plus this random perturbation. Now, I promised you to dwell on the independence. So for every I like this, if this is Y, so this red one is this vector, then what we require it is that these vectors are independent, and these vectors are independent copies, the copies of this random vector y1 by L. So we do not assume that the components are independent. It will be important for us later, because then we can apply it in a more general way. So how all of this look like? What you can do it is that you can choose alpha beta, this interval I. Alpha beta is just a big interval such that regardless the random error, I is sent into its interior. So alpha beta is a big interval which satisfies this, and then basically these are the cylinders, the first cylinder intervals, and then the random translation parts are these Y parts, and the T1, T2, T3 were the translations. So we can imagine that here is T1, and then this random translation makes the left-hand point not T1, but somewhere here. And if this is T2, then because of this random translation, this second cylinder doesn't start exactly at T2, but a little bit off. And then this is T3, but because of the random translation. And in every interval, we repeat not the same picture, but the same process. So this is basically how this, in every step when we apply these functions, so this is probably the good formula to remember, that if it was deterministic, then these Y's were not here. And these Y's are the random translational errors. And because of these random translational errors, this is going to be a random mapping. And with this random mapping, we take the image of this interval alpha beta, and the images are the first cylinders, and then similarly we construct higher cylinders. Okay, so I wanted to write all of this down with some formula. So if we are given self-similar iterated function system on the line, and the alphabet is 1 to L, and I is a compact interval with this property, and then lambda hat, this is the deterministic, the union of deterministic and cylinders, and this is the deterministic attractor. Then the random perturbation lambda of this deterministic attractor is when we replace these deterministic functions as I with these random functions, and then we form these intervals, these cylinder intervals, and then the union of level n cylinder intervals is the nth approximation of the attractor, and the intersection of this n is the random attractor, the random self-similar set under consideration. So now I can state our theorem that the similarity dimension of the randomly perturbed iterated function system is the same. So this is not the theorem. This is because what is the similarity dimension? The similarity dimension is the solution S of this yellow equality, this yellow equation. And here we always add a translational error. We do not change the contraction. So one more time, what was these lambda i's? Just like to go back. Lambda always means for me the contraction, and t means the translation, and y means the random error that you add to the translation. You add the random error to the translation. You do not change the contraction ratio. So for this randomly perturbed system, the similarity dimension, which is the sum of the absolute value of the contraction ratios raised to the power s equal to 1. So the solution of this equation for the randomly perturbed system is the same as the deterministic deterministic system. And our theorem says that if this s is bigger than 1, then actually the interior of the random attractor is not empty almost surely. I would just like to go back to the first slide when I mentioned this problem, that if you consider a self-similar iterated function system on the line, whether or not it is possible that the self-similar system has positive Lebesgue measure and empty interior. We do not know. This is a very challenging and very beautiful, very important open problem for the deterministic systems. We don't know the answer, not even after our paper. We do not know the answer for this original question about deterministic self-similar sets, but our goal was to construct this kind of randomly perturbed system and answer the question for this randomly perturbed system. And this is what we did, that if the similarity dimension is bigger than 1, then the interior is not empty. Now, what happens if the similarity dimension is smaller than 1? If the similarity dimension is smaller than 1, then there is nothing to do. The Hausdorff dimension is smaller than 1. So in that case, there is no interior point. So this is what we can see. And then our motivating, so the reason that we consider this was not only to answer this randomized version of this open problem, what I mentioned originally, but there was an old problem of polystockens. This problem of polystockens was something like this. Is not very precisely stated that if you have two dynamically defined Cantor sets on the line and you consider their algebraic difference. So what is the algebraic difference? Is the collection of points which can be represented as the difference of the elements of this set. So this is the so-called algebraic difference. And the question of polystockens was that if you have a dynamically defined, it's very important, dynamically defined, so you have dynamically defined Cantor set C1, C2 on the line, whether or not it is true that their algebraic sum or difference, doesn't matter, sum or difference, it is the same, because what is the algebraic difference of C1 and C2? You take C1 cross C2 and the 45-degree projection of the product, and then it is the difference. But if you take the 45-degree projection in the other direction, let's say 135-degree projection, then it is the sum. So doesn't matter sum or difference. So this question of polystockens was that if their dimension are bigger than 1/2, whether or not it, so sorry, the question originally was that you take the algebraic difference, then this algebraic difference typically, it's important, typically is either large in the sense that it contains interior point, or it is small in the sense that its Lebesgue measure is 0. So not intermediate, typically not intermediate. Intermediate set would be that its Lebesgue measure is positive but contains no interval. So this was the conjecture of polystockens, and that was our motivation to investigate this conjecture for this randomly perturbed Cantor set. So C1 and C2, two independent copies. And then we need to assume that the similarity dimension is bigger than 1/2, because otherwise there would be no chance that this contains interval. If S was smaller than 1/2, then we had no chance. So we assume that they are independent copies and their similarity dimension bigger than 1/2. And the previous theorem implies that then this algebraic difference contains some intervals. And we get this conclusion from the previous theorem just because if you consider this kind of sets which was introduced over here, this kind of random sets like this lambda, then the good thing is that the algebraic sum will be also in the same family of random sets. So the algebraic sum of two elements of this family is also an element of this family, And in order to provide that, this was the point when we needed to be a little careful when I said that we do not assume that these in the random translations, these components, we do not require that they are independent, but we require that these error vectors are independent for different I1, IK1, but just the vectors are independent, and it is not required that the components are independent. And that's why any iterate of such random set is in the same family of random sets, and the algebraic sum is also in the same family, and that's why the previous theorem can be applied, because if C1 and C2 two independent copies of this attractor and the similarity dimension is bigger than 1/2, then the C1 minus C2 will be in the also a self-similar, randomly perturbed self-similar set, but in this case the symmetry dimension will be bigger than 1, and then we can use our main theorem that if the symmetry dimension is bigger than 1, then the attractor contains E interior almost surely. So these were our results, and I just like to make a couple of comments. Similar random perturbation can be defined not only for self-similar iterated function system. I just like to come back to this page. When I wrote it down, this was a self-similar system, but if this iterated function system is not self-similar, but self-affine, self-conformal, anything, just iterated function system, which means that the finite collection of contracting mapping, the only thing that important that these mappings are contracting, any finite collection of contracting mapping, you can define exactly in the same way this random translational error gives you a random perturbation of the system. So in particular, if this system is not self-similar, but it is self-affine, then you can do the same, you can conduct the same construction, which was done by Jordan, Polycott, and myself almost basically 20 years ago. When we wrote it down, it was 20 years ago, I'm sorry. And then in that paper, which was about in higher dimension, not dimension 1, and self-affine sets, in that paper, well, the result of that paper can be applied here, just for d is equal to 1, and that the result of that paper basically gives that if S is bigger than 1, then the attractor has positive Lebesgue measure almost surely. So this is a very, very special case of our result in higher dimension, but we get from our result that the Lebesgue measure has positive, the attractor has positive Lebesgue measure. What we did here with Székely, Szekeres, and Decking, our paper is Székely, Szekeres, and Decking, but give more, it is not only that the interior is not empty. Well, sorry, not only that the Lebesgue measure is positive, but also that the interior is not empty. So we managed to prove this only for similar case on the line. We did not consider the self-affine case. In the self-affine case, the same question could be asked if you you are given a self-affine iterated function system in RD, as in our paper with Jordan and Polycott 2007, you are given, and what we proved it was that the Lebesgue measure is positive if the so-called affinity dimension is bigger than the dimension of the D. We proved that the Lebesgue measure is positive, the Lebesgue measure of the attractor is positive. After our result here, this result, it is natural to ask whether similar thing happens in the self-affine case in higher dimension. We did not prove that. We just worked on the line. So maybe I would talk a little bit, I would be a little bit more specific about this random perturbation for the first. Just to be more specific about it, the random vector, so here L is an integer, at least 2, and A is the alphabet, and we consider this random vector, and then yi are continuous random variable, and the random variables with continuous density, and the density is positive and bounded on this interval and 0 outside of this interval. And then we let capital T the L array tree, and this is the root, and the level and nodes of the L array tree are these I1, In, and we consider a randomly labeled version of this T. So this randomly labeled version for every node I of this tree, so I is just something like this, for every node, we are given such a vector. So in every node, a vector, the translation vector is sitting, and the translation vectors which are sitting there are IID, so they are independent. The vectors are independent, and they have the same distribution as this y1 to yl, and then the corresponding probability space is omega, which is like this, and then the canonical sigma algebra is considered, and the measure is the product measure. This gives the independence that this is, but the x is the probability distribution, so the probability distribution of this yi. Okay. And then I would like to say a couple of words about the proof. So here this should be not Ri but lambda I. I wanted to lambda I. So originally, so we can go back to our setup. The setup was like we have this lambda I x plus ti. So first of all, and our assumption is that the similarity dimension is bigger than 1. So first of all, we realize that we may assume that all the contraction ratios are the same positive number. We may assume this just by losing a little bit of similarity dimension. So our assumption is that the similarity dimension is bigger than 1. Then what we can do is we can go to a higher iterate, and this is the moment when we use that for such a random iterated function system, any higher iterate is still in the same family. So we go to a higher level, we take all level n iterates, it is the same kind of family, and we just obtain a big subfamily when all the contraction ratios are the same. And we can do that And we can do that in such a way that we do not lose much on the similarity dimension. This follows from a theorem of Farkas. This follows from a theorem of Farkas, which theorem was an improvement of an earlier theorem of Schmerkin and Perez. So what I want to say is that the original system that we consider is not a homogeneous system, but we may substitute with a subsystem of a higher iterate, which subsystem is going to be eventually homogeneous, and that's why we can assume this is not Ri, sorry, this is lambda. All the contraction ratios are sorry, non-negative and the same. This is the first observation. And what we do it is that we would like to use a theory of branching processes, quite advanced theorems. But in branching processes, individuals have children. So I would like to explain on this picture what does it mean that x1 and x2 are children of x. So here is the point x, and this is the situation. Here are these random translations of the cylinders, and you see that this x appears in this cylinder interval and this cylinder interval. Now, if you renormalize, renormalize means that you extend somehow this, you blow up this I1 to this original interval I, and you blow up I2 to the original interval I, then this small red, because this point corresponds, if you blow up I1 to I, then you see that this purple interval over here, it goes to this purple interval, and that's why one of the children of x is this x2, and here you see this gray interval, and when you blow up I2, then it will be. I should have named this x2 and this x1, doesn't matter. So it's just you see that because of these 2 points, what you see over there, and when you blow up this interval to the whole, then this gray blows up to this gray interval, and this purple blows up to this one. That's why these 2 people, x1 and x2, are children of x. Now, if x is a point from the attractor, and then the fact that x is from the attractor, it means that x is in the nth iteration of the attractor for every n. Now, if x is in the nth iteration, then x is in one of the level n cylinders like this. This happens, so x is in one of the level n cylinder because this I is equal to this random set. But this means that the inverse of fi applied on x is within this interval I. So that's exactly what I wrote down, that if you take for this x f1 inverse, then it comes to here, and f2 inverse, it goes to that. So this is the meaning that x1 and x2 are children of x. Just a moment. It doesn't want to do what I want. I'm sorry. Okay. So x is in lambda, and if and only f, it has at least one level n offspring. Actually, what we can check, it is not that exactly one, but there are at least exponentially many level n offsprings. So what we do it is that the main steps of the proof. I just like to give some ideas. So one difficulty of the proof is that we need to prove the existence of a set T, which is going to be called the time space. Time space. This will be a branching process with uncountably many types. So T is a type space. This is the
It's being
do you hear me? Because it said that it stopped. Could you confirm if you hear me?
Your sharing screen went away, but we could hear you just 1 minute back.
Okay, so I should go 1 minute back because it died. I'm sorry for hearing that. So
We were with you till 15th slide.
Pardon?
We were with you till the slide number 15.
Slide number 15. Good. So what I want to say it is that what we need to prove.
Could you please share the screen?
Share the screen. It is not shared. Oh, yes, because is it okay now?
Yes.
Very good. Thank you very much. You know, I am in China. I am not home, and I have internet, but this internet is not as strong as the one in my home. So I hope that without too much further interruptions, we can go. So the main step of the proof, so what I started to say it is that if you have such an x, then these x1 and x2 are the level 1 children. But in order to provide that x is in the attractor, x needs to be in the nth approximation for every n. So x need to have a level and child. But you cannot prove that there is exactly one level and child. The only thing which is realistic is that you would like to prove that you have exponentially many Lagrange children, and then this is what we would like to do. And somehow the key step is the verification. Then this big interval, within this big interval, there is a subset which is capital T, which is the finite union. So these two blue big intervals, this is the union is T, and this blue union of blue interval have this subset, which is W, and then T is the theta neighborhood of W for some positive theta, whichever. So we need to prove the existence of W and T in such a way that whenever you choose an element X from this big one, the big one is the blue. You choose an element of the big one from the blue, then the expected number of level R children, so we need to prove that there exists such a level R, doesn't matter, level 1, level 2, level 33, but we need to prove that there are these intervals, the union of the blue interval and the union of the red, and the red is smaller than the blue, such that if you pick a point from the big one, from the T, which is the big one, then the level R offspring contained in the small one. So maybe you choose an X from here, what I show, which is in the big one, but not in the small one. Nevertheless, this X, what I show you, has at least 6 children on level R in the small one. This is what we need to prove. This is the key. This is the key point, basically. And if we can prove this, this is not easy to prove this, but if we can prove this, why it is good? Because these mappings, although here you have these random translation errors, but these mappings are contractions. And if you have, so what does it mean that it has 6 children in W? It means that at least 6 words, I1, IM, such that this is in W. And then if you choose a point close to Y, as close as this, then its inverse is going to be theta closed. This is smaller than theta times, then this is theta closed, and that's why it is in T. So one more time, if you choose a point which is in T, and it has at least 6 level R children within W, then everybody which is theta close to this point, what I show you, has also 6 level R children, not within the red, but within the blue itself. So the children of X needs to be within the small, within the blue, such that if you take a very close point from X, its children will be corresponding children will be not in the small, but at least in the big one. Somehow this is the reason for which we needed the small one and big one. Now, the way as we argue is as follows. We know that the simulated dimension is bigger than 1. And if it holds, then L times A is bigger than 1. L was the number of mappings, and A is the contraction. And then by pigeonhole principle, what we have it is that there is an interval, this J interval, such that there are exponentially many level n intervals above, which contains this, just because of this inequality. So here there are exponentially many intervals. It means that every point from this red have exponentially many level n children immediately. And then let's say this exponentially many means that b to the power n, these are the level n children what we have. But then they have let U1 be the total number of level R offsprings of these level n children, level R offspring, within W. W was the smaller interval. Then we use a version of large deviation theorem, which says that there is a tau from 0, 1, that the probability that this U1, this total number of level R offsprings of this exponentially many level n children, that this number is smaller than 4 times b to the power n, this is tau raised to the power b to the n. So the probability that U1 is smaller than this exponentially big number is super exponentially small. So the probability that it does not have at least this many level n plus r offspring is super exponentially small. And then we can extend this, as we discussed it earlier, to every element of this interval J. We can extend this idea. So and then we apply this for a grid of exponentially many elements, and what we get it is that exponentially large number times super exponentially or probability covers the bad situation, and somehow this leads us to the fact that with very high probability this bad interval is going to be contained in the attractor. Now, I would like to mention, so our argument was entirely related to branching processes, so the theory of branching processes, and then there was a more recent paper by Balázs Bárány and Mihály Ramszi, Probability Theory and Related Field 2025, and they proved more with under stronger assumption. Their terminology is a little bit different. I'm not sure that I really have time to go through exactly on their terminology, but I just like to tell you that in our case, when we spoke about
Professor
these,
Simon?
Pardon?
Yeah, we have only 5 more minutes. Like we
Thank
want to
you
give
very
5 more
much.
minutes for the question answers, so we have 5 more minutes.
Okay, I just like to say 2 or 3 sentences.
Yeah.
So
Yeah,
it's
sure.
we do not need that these translations are independent. We just need that translation vectors are independent. They needed that all the translations are independent, and under that assumption, what they proved it was that if you take a measure on the symbolic space and you push it forward, then the push forward measure will be absolute continuous with respect to Lebesgue measure with Hölder continuous density almost surely. So basically what they need to assume it is also that the similarity dimension is bigger than 1, and if you have similarity dimension bigger than 1 and you have a Bernoulli measure on the symbolic space and you push it down, then you get a push forward measure which is absolutely continuous with Hölder continuous. The point is continuous density, and in this way it also gives what we already proved, the existence of interior point. Thank you very much for your attention. Finished.
Yes, thank you. Harsha, any update? I'm stopping the recording and